Okay, so what we've done in the last segment was to use the Legendre transformation, the notion of our Helmholtz potential, and the Clausius-Duhem form to make certain observations about constitutive relations, right, for ongoing processes. Most significantly, we arrived at the Fourier law of heat conduction, right? Or rather, stated better, we found that the Fourier law of heat conduction satisfies the Clausius-Duhem inequality, and therefore it is physically admissible. Okay, so let's proceed and get back to the balance of energy and work with it a little more. Okay, so now let's recall our equation for the balance of internal energy. And remember that this is just our first law of thermodynamics. Okay? So the form in which we left it was the following. Material time derivative of the internal energy equals the local heating minus divergence of the heat flux plus the stress power. I am straight away going to multiply this relation through, this equation through by the determinant of the deformation gradient, so that I can now write this as rho naught material time derivative of internal energy equals rho naught r bar minus the Jacobian Jacobian multiplying the minus divergence of Q plus J sigma contracted with D, and we observe that because we have J sigma, this is just tau contracted with D, but we also know that this is S contracted with E dot. All right? Okay. We're now going to reintroduce to this equation our Helmholtz potential and the entropy. Okay. So, use E bar now equals, sorry, not psi bar. E bar is equal to chi bar, our Helmholtz potential, plus theta eta bar. Okay. Observe that this is just the Legendre transformation written differently. Okay. When you use this here, what we get is rho naught material time derivative of chi bar plus theta material time derivative of eta bar plus eta bar material time derivative of the temperature. Okay. This is equal to rho naught r bar minus J divergence of the heat flux plus S contracted with E dot. Okay. All right. What I'm going to do now is expand out this term, okay, using partial using the chain rule. Okay. And to do that, I'm going to remind ourselves that chi bar is a function of E, the strain, and theta. All right. So What we get here is rho naught partial of chi bar with respect to E contracted with E dot plus rho naught partial of chi bar with respect to theta times material time derivative of theta plus rho naught theta partial of material time derivative of eta bar with respect to time plus eta bar material time derivative of theta, and I think I need to have a rho naught here as well. Okay, all of this is equal to rho naught r bar minus j divergence of q plus s contracted with E dot. Okay. Now, in the last segment, we demonstrated that this is S. Okay? Also, we demonstrated that this partial of chi bar with respect to theta is minus eta bar. Okay? What that lets us do is to observe that this term cancels out with the stress power and this term cancels out with this one. Okay? Right? All right. So, we have this, and let's move on from here. Okay? What we are left with is just 3 terms in our first law. Okay? There is this term which survives, and these 2. So let's group them and write them on the next slide. We have rho naught theta material time derivative of the entropy equals rho 0 r bar minus j divergence of q, right? Divergence of the heat flux. Okay, what else can we do here? We can recall our constitutive relation for eta bar, and that constitutive relation is the following. It tells us that we have ddt here of eta bar, but eta bar is minus derivative of chi bar with respect to theta. Okay? All right, but now in order to take this derivative, okay, we already have this first derivative with respect to theta. In order to compute the time derivative, what we observe is that we must have rho 0 theta. Okay, we are going to apply the chain rule once again in order to compute this material time derivative. Okay, so we have rho 0 theta, we have minus derivative, the second derivative of chi bar, but this is a mixed second derivative. Okay, and we have another term which is the second derivative of chi bar with respect to theta material time derivative of theta equals rho 0 r bar minus j divergence of q. Okay, I'm going to reorganize this thing once more. On the left hand side, I'm going to leave rho naught theta. Well, let me incorporate the minus sign here, and I will have partial of chi bar with respect to theta square. Actually, I've changed my mind. I'm going to put the minus sign inside. I'm going to put the minus sign here, and just because I'm allowed to, I'm going to put parentheses there. Okay, d theta dt. I'm moving this mixed derivative term to the right hand side. So I got rho naught r bar minus j divergence of q plus rho 0 theta second derivative of chi bar with respect to theta with respect to E contracted with E dot. Okay, this I claim is our heat conduction equation, okay, or heat transport equation. Observe what it, so let me write this down. This is our heat transport equation. So what is it telling us? It's telling us that the rate of change of temperature is driven by a bunch of things on the right hand side. Okay? It's driven by the rate of local heating, which is not surprising. Yeah, we understand that. It's also driven by the heat flux, right? The heat flux, the divergence of the heat flux, which we know from arguments that you've definitely seen at some point in your undergraduate studies, maybe in mathematics, maybe in physics, about how the divergence of a vector really tells you that the net outflux, right, over some little unit volume. Since this divergence term has a negative on it, it gives us a net influx of heat. So what it's telling us is that when we have a little elemental volume, this influx of heat is contributing to the change in temperature, right? The third term is, actually let me label these terms, okay? I don't think any, well, let me write this also. Rate of temperature, okay? This term is local heating, okay? This term is net influx of heat. This last term is a special one which needs a little more work. Not work, but it needs a little more explanation. For now, because it has that mixed derivative with respect to temperature and strain, it should straight away tell you that it is telling us something about the coupling of thermal and mechanical fields here. Okay? It is what we will call elastic heating. Elastic for obvious reasons. It's a, we've already established the fact that the derivative of chi bar with respect to E is the stress. Okay, so clearly there's an elastic effect there. But it shows up on the right-hand side and it is contributing to the temperature rise, so it must be doing something to it with regard to heat. Okay? Finally, let me state that this product, you recognize that product, theta with the minus second derivative of chi bar with respect to theta. The temperature times the negative second derivative of the free energy with respect to the temperature. Do you recognize that term? This is your old friend or maybe nemesis from your study of heat conduction previously, which is the specific heat per unit mass. So let me say a little more about just that last term. If we say that, if we look at chi bar and we are looking at, let's suppose that we're looking at how chi bar varies with theta. Yes, it's a function of E as well, okay? But let's suppose we're looking only at how it varies with theta. What we are saying there is, because if the specific heat is a constant, is a positive quantity, what we are saying is that if the specific heat has that type of dependence with respect to theta, okay, it has a negative curvature. So what this implies is partial of chi bar with respect to theta, second derivative of the second derivative of chi bar, second partial derivative of chi bar with respect to theta with a minus sign is greater than or equal to 0. Okay, so if the specific heat, if the free energy, the Helmholtz free energy has this type of dependence with respect to temperature, we have a positive specific heat. Okay, right? Okay. So, so we can now rewrite, what I'm going to do is to say that, well, if we denote rho naught theta times minus second derivative of chi with respect to this as the specific heat per unit volume, okay, right, and we denote it as let's say C. Once again, we C is just a natural thing it's just a natural symbol to use for this. Hopefully we don't get confused with our spatial tangent, right? This is a scalar, so there's no question of, I don't think there's any risk of getting confused. Okay, so what this then tells us is that now we have C d theta dt equals rho 0 r bar, temperature rise from heating, local heating, minus J divergence of Q, temperature rise from local heat influx into a little volume, plus, okay, rho 0, second derivative of chi, I think there's a theta here as well, second derivative of chi bar with respect to theta and E, contracted with E dot. Okay, we're going to stop here in this segment because when we come back, I want to say a little more about elastic heating. Okay, but the thing to take away from this segment is the fact that our first law is indeed what gives us finally our equation for heat transport. And you will recall from the very first segment, when we started talking about continuum physics, we did refer to the equation for heat transport back then. Okay, so we've arrived at it. All right, we'll stop here.